first and foremost, congratulations to everybody. You've all done a great job by the sounds of things, and well done to the winners. But everybody's a winner as far as I'm concerned, because anybody who does science is fantastic in a science project. I'm a scientist myself. I'm going to give you a bit about my own background and how I got into science. And then I'm going to give you one story about my own research is what I'm going to do for you today. Now, my name is Luke O'Neill. There's my name, and I'm in Trinity. I'm actually an immunologist, is my profession, working in the School of Biochemistry and Immunology. And I have a lab here behind me, out the door there. There's 12 people in my research group. And we all investigate one thing, and that's called inflammation. And I'm going to give you a bit of a background on what that is and the kinds of things that we're trying to do. But my own journey, no more than everybody involved in SciFest, began in school. I had a fantastic biology teacher. I went to Pres Bray. I'm from Bray originally. And my teacher got me into biology. And again, credit to all the teachers too. I'm sure there's some teachers will watch this as well. Teachers are extremely important. And this particular teacher, Fran Mooney, got me into biology many years ago. And then I decided to do biology in university because I loved it so much. And there's a message, everybody. If you love science, pick it as a thing to do at third level. And it can be any subject really, but of course we're here to talk about science mainly. So I found science fascinating, one of those things. And in particular, I found biology fascinating. So I began doing biology. I ended up doing a degree in biochemistry. And biochemistry is the sort of chemical basis for life, which really fascinated me. And then I got into diseases eventually. And trying to understand, I suppose, the chemical basis of disease became a big focus for me. Did a PhD, which is often the entry-level qualification, actually. If you want to be a research scientist, you do a thing called a PhD. And that's when you do real research. And my research project was on a disease called rheumatoid arthritis, which affects your joints. People may have heard of it. It's inclined to afflict older people, where your joints get very stiff and sore and painful. And I worked on the scientific basis for that. Could we understand what's going wrong in the body in that disease? And of course, the ultimate goal being, can we actually come up with medicines to treat that disease? And that's my big topic. I've always worked on these so-called inflammatory diseases for many years now. And I'm going to give you one story on a new drug that we discovered in my own lab, actually, that's now being tested in patients. But to get to where I've got to, you've got to do science in school, obviously. You'll do biology in the leaving cert because it's a biological area. It's about living systems. Then you might pick a degree in a relevant area. And if you want to be a research scientist, you might do a master's or a PhD. It sounds like a painfully long road, but it's great fun. Remember, because you're doing something you love. And there will be ups and downs and challenges. But overall, I've nothing to regret here. I've had a great time in my career so far and still very much active in trying to understand the biological basis of these diseases. Now, my title here I've given you is, will we cure all diseases by targeting inflammation? Now, there's a bold claim. Can we cure diseases by targeting one thing in the body? And you will all know about these diseases. They're very common and they afflict so many people. So the big focus are these inflammatory diseases, and I've worked on them for many, many years. And there are several of these, and you will all be familiar with them because I bet someone in your family might have them, or you might have them yourself. You never know. And what happens here is your own immune system, for unknown reasons, begins to attack your own body. And of course, the immune system evolved to fight infection. And I guess you may have heard of the immune system as a thing that fights bacteria, it fights viruses. It's got very powerful weapons to fight those germs. And of course, during the COVID-19 pandemic, it was a big focus for many of us because we needed our immune systems to fight that virus. The trouble is, in lots of diseases, it turns on your own tissues, and we don't fully understand why. So for example, in your brain, if it attacks your brain, that would be multiple sclerosis or Alzheimer's disease or Parkinson's. You might have heard of those. If it's in your joints, it's arthritis, as I mentioned already. If it's your skin, it's a thing called psoriasis or eczema, for example. If it's in your stomach, it's a thing called colitis. And all these different diseases, the immune system attacks your own body, and that attack then damages that part of the body, and then you get the symptoms. And there might be pain. It might be swelling. It might be a part of your body won't work as well because of all this inflammation that's going on. And that's the thing that I've been studying for, I guess a long time, for several years now, to try and understand what's going on in those diseases. And I've worked on the following diseases: Parkinson's in the brain, asthma, that's in your lungs when you can't breathe properly, heart disease, where the heart gets inflamed and attacked, multiple sclerosis is in your brain, atopic dermatitis, that's in your skin. And all of these involve this inflammatory process that seems to be going awry. Now, before I get into it, though, I've got to tell you this story because this is one of the greatest scientific stories ever told. And I tell it as an immunologist. And it's relevant because it's about the immune system as well. And it's about the COVID-19 vaccines. Now, these are a fantastic discovery. And I guess people may remember the COVID-19 pandemic. It's a great story because the virus was first found in early January 2020. And I guess some of you may remember that. The trials for the vaccines began within about 3 months. And by December of that year, less than a year, the first vaccine was approved. And that's a remarkable success story because the vaccines, remember, vaccines get your immune system to recognize and destroy germs. It really helps your immune system do its job. And the very first person to be vaccinated was an Irish person, actually, Margaret Keenan in the UK. And there she is taking the very first vaccine shot. That was the Pfizer vaccine. And remember, those vaccines have saved 20 million lives in their first year, 1.5 million lives in the EU. And this is a scientific fact. And there would be people, criticizing vaccines and have issues about them. This is scientifically true. We use data, we use careful observation to come to a scientific conclusion. And this is what's happened here. Now, can you imagine a situation where there's a war going on? And I offer the government of a country a weapon to save 1.5 million people in that war. That government would bite my hand off, and that's what these vaccines did. They saved and continue to save an awful lot of lives. And vaccines are interesting if you're an immunologist because they're designed to help the immune system fight a given germ. And we need new vaccines, by the way. We've no effective vaccine for malaria. You may have heard of that. That's the thing that happens mainly in the tropical world. TB is a big disease, no real effective vaccine. So we need to get new vaccines, and we need science to discover those vaccines is the important message, because you know what? Science is great. And I'm sure you all agree with this, being part of the Sci-Fest. And I wrote a book which conveys how great science is. It's never mind, that could be pronounced bullocks if you wish. And never mind the bullocks, here's the science, and it's all about how great science is. And I show you this because at the start of the book, I quote Marie Curie. And she had a great quote, She said, "Nothing in life is to be feared. It is only to be understood, It is only through understanding things that we may fear less." So what science does is it banishes fear. That's a real job of the scientist, actually, is to discover things that help us not be frightened. And if it's an infectious disease, you discover a way to develop a vaccine to take the fear away from COVID-19. If you're an immunologist like me, you're trying to discover ways to take the fear from diseases. Because if you're told that you have a disease, it's frightening, and science is helping to come up with ways to stop these diseases is the overall idea. Now, Marie was an amazing woman. Stadowska Curie, you may have heard of her. She discovered radioactivity and radiation. What a fantastic discovery that was anyway. And she won 2 Nobel Prizes, which is quite remarkable. She realized, actually, she was the first to describe radioactive elements. Worked on polonium, named after where she came from, Poland, actually. Also found radium, radioactive element. And it was exciting science. But she also wondered, could this be useful? And guess what Marie Curie proposed? Use this to fight cancer. Because radiation can burn tumors. And nowadays, we use radiotherapy, the highly effective power within radioactive substances to burn tumors. And Marie Curie was very much part of that. Very interesting woman, her life. I'd recommend you to read it if you like. And then her daughter, Irene Joliot-Curie, guess what? She won a Nobel Prize as well. They must have been some family, all those Nobel Prizes, but they're very important in the history of science, especially Marie Curie. Now, I didn't work on radioactivity, obviously enough, but I was fascinated by the likes of Marie Curie, and my book describes all those interesting, fascinating things. What I work on, as I say, is inflammation. I'm working on a new book. It'll take me 2 years to write it on this process of inflammation because it's so important. And as I've said, it's the root of most diseases. Your brain can be attacked, your skeleton, your joints, your skin, your shoulder, or any part of your body can be attacked by your own immune system, causing all the pain and swelling and soreness in these diseases. And basically, it's a normal process that happens if you sprain your ankle. It's a bit sore, and a bit hot. That's good. The ankle gets repaired. In these diseases, it's like an ankle that won't repair after it's been sprained, but it's a part of your body that's being afflicted, and we'd love to know why that is. And we've discovered a lot about the parts of the body that are getting sort of damaged and the different component parts that are going wrong. And the big challenge has been, as a scientist, can you figure out which parts of the immune system that's driving inflammation is now misbehaving in these diseases. And there's loads of parts. It's very complicated. It's a great thing to get involved in. There's all these different component parts. And we've worked on one particular component part. And it's called, get ready for this, NLRP3. Now, there's a horrible mouthful for you. And one challenge we have is the terminology we use is often impossibly complicated, and we apologize for that, but things have names. What is NLRP3? It's inside white blood cells. Now, these cells here, these 3 cells, are called macrophages, and they are the cells we work on in my lab. They're in your blood. They're the front line of the immune system. Macrophage means big eater, right? And they normally eat bacteria. They eat viruses. They're patrolling your body, eating up the bad guys, right? But they also eat noxious things that build up in your body. So, for example, bits of proteins can build up. Metabolic products, they're called. That would be things like cholesterol. You might have heard of that. That builds up in heart disease, you know. A thing called uric acid builds up in gout, right? And it turns out the macrophage eats those because its job is to eat stuff. The trouble is there's too much of this stuff, and now the macrophage goes into overdrive and causes massive inflammation that becomes damaging. And it drives quite a complicated pathway. I won't go into the details, but downstream of this, there's various other components that get triggered by this. And my lab began working on this, about 15 years ago now. It was discovered by a Swiss scientist called Jörg Schopp and a Californian scientist called Hal Hoffman. They're friends of mine. They were the ones who first saw it. Now, can you imagine the thrill of discovering something brand new? And remember, that's what scientists do. Your job is to discover brand new things. It can be anything. It can be dinosaurs. It can be stars. It can be the Large Hadron Collider. Who cares? They're all part of science, right? In this particular case, those 2 people find a very important part in macrophages that drives these macrophages into overdrive. And here's examples again. There's cholesterol. You may have heard about that. That's in heart disease. Here is uric acid. That's in gout. Now, 2 very important diseases. Alzheimer's disease. That's a protein, a normal protein called beta amyloid, builds up in your brain. The macrophage goes in, tries to clear it, and explodes because it's overactive, and that damages that part of your brain. And beta amyloid is in where you make memories. So that's why you see memory loss. In the case of Parkinson's, it's another protein called alpha-synuclein, another horrible mouthful. That builds up in the part of the brain that controls movement, and that now gets destroyed by your own immune system because this stuff is building up. We'd love to know why these things are building up, by the way. We don't know. That's another mystery. We need research and scientists to try to find that out. But the bottom line is NLRP3 is sensing these things, going into overdrive, and then damaging the part of the body where it's being overactivated. Another analogy I use is dominoes. Some noxious thing. This could be, beta amyloid or cholesterol. NLRP3 gets knocked over, drives all these events that culminate in disease. And of course, we'd love to block that. That became a goal about 10 years ago now, I suppose. Lots of drug companies try to develop drugs to block it. If you stop that domino falling, you'll stop this sequence of events that culminate in diseases happening. It's a bit like a vacuum cleaner. Analogy number 3. We scientists, we love analogies. It's a bit like a vacuum cleaner. It's like the macrophage. The trouble is it overheats. It's trying to hoover up this stuff, and now it overheats and causes all the damage. And we found a drug to block it. Now remember, I'm talking about a drug to block that NLRP3 protein, and we found a drug, and there it is. Any chemists, anybody interested in chemistry? There's a few carbons and sulfurs in this molecule. That's the drug that blocks this NLRP3 protein. And what was amazing was that we find the drug randomly, it must be said. It had been found in the 90s as an anti-inflammatory. People didn't know what the target was. We wondered, would NLRP3 be the target? And lo and behold, it was. Now, that molecule, I'll show you again. Very simple structure. It's not that complicated. That will stop disease in mice. Now, we often use animals sparingly, it has to be said. We try to avoid using them, but we use them as models of disease before you go to human, because it's too experimental to jump into humans without proving things in what I call animal models first. And there are models of many diseases. You can give a mouse Parkinson's, you can give it Alzheimer's, you can give a motor neuron disease. All these diseases, our drug stopped the disease in the animals in its tracks. Now, you can imagine that's a very important discovery because it suggests it might work in humans and identifies the thing as being important. And it worked in asthma, it worked in gout, it worked in heart disease, it worked in MS, it worked in colitis, psoriasis, a thing called lupus. All of these inflammatory diseases involve NLRP3 out of control, and this drug can prevent that from happening. And how do we develop that further? Well, we founded a company out of my lab in Trinity called inflammasome. And very often we will form companies to develop things because you got to be able to get money in and develop them and research them. And again, anybody interested in science may end up working in a company. It could be a big drug company, it could be a small company. Ours was quite small. And you need companies to invest and get equipment and what we call commercialize, bring to the market. And we founded a company called Inflammasome. Matt Cooper was my key collaborator. He's a chemist. Jeremy Skiddington was our head of business. All of us have PhDs. Jeremy got a PhD and then went into business, the business side. Matt was a chemist. And we raised some money from various investors and Inflammasome got going. And we built a team of people. And look at this, there's chemists here. There's a chief medical officer. There's people involved in things like clinical operations. You need a big team of people. All of them have science degrees, very importantly. There's many jobs in this business to get all these different fantastic experts all working together and collaborating to try to make this thing a reality. And we ended up with two drugs, IZD1774 and IZD334, that we developed that stop NLRP3. And then guess what happened next? A big Swiss drug company, Roche, they're in Basel in Switzerland, one of the world's biggest drug companies. They took our molecules, and we needed them because they're a big drug company. They can do trials, they can invest, and they've just finished in the past few weeks, hot off the press, 3 trials in humans with our drug. And what diseases have they chosen? Now, remember, I gave you a big list of diseases earlier that could involve NLRP3. They've chosen Parkinson's, heart disease, and asthma. And this is a poster they just released. Here's Parkinson's. The brain gets damaged, gets inflamed. Our drug blocks NLRP3. And the big question is, if you stop all the damage, will you slow the disease down? Because you're stopping all the burning of that part of the brain. And they haven't told us the data yet. It's quite frustrating. We're waiting to hear if it worked. There's a hint it may have worked in what's called a phase 1 trial. It'll move through now, phase 2 and phase 3. It takes different phases to get a drug eventually discovered. You're looking to see if it works. And secondly, any side effects, because often drugs have side effects you can't predict. Hence, you've got to do these clinical trials. So we're now on the way with this drug. Can you imagine if we get an effect here? Now, remember, it's a lot of effort and many drugs fail. In fact, if you get to the phase 3, the last phase, half the drugs fail. They fail because of some side effect that you didn't expect, or sometimes the target isn't as important as you thought. Again, you got to use science to get the evidence and the data to dig into these things and provide support that we need to examine these in more detail. But still, we're underway now. And here was the trial in Parkinson's. It's such a thrill. Remember, this began in my lab. Just behind me here, we found this drug. They tried 39 patients were given the drug. And of course, you have 18 on placebo. You got to have a group that are on a dummy pill. And you compare the two. And of course, any difference you're hoping you'll see. It's double blind because nobody knows who's on the drug and who isn't. And it's placebo controlled. It means you give a dummy pill to some of the people, but nobody knows. All the pills look the same. And the doctors don't know who's getting what, and the patients don't know. It has to be completely unbiased. And now we're waiting to see in this group, the ones who took the pills twice a day, will we see any effect is what we're asking at the moment. And they just released this. What they've said is, Roche, researchers found a difference in the level of a marker that appears in higher amounts when there's inflammation in the brain between people who took selnoflast, the study treatment, and those who took placebo. This means that selnoflast reached its target. So they've managed to suppress the inflammation in the brain of Parkinson's patients. Now, it was only a 4-week trial. We're waiting to see if it affects, obviously, symptoms. But you'd be hopeful now that you should slow the disease down because you've seen you're putting the fire out in the brain with this drug, And the hope is that will translate now into stopping the disease progressing and getting worse. But we don't know yet. It's still very early days, and we're waiting for the next trial to happen. And what's very exciting as well is we published our paper on this in 2015. So it's a long old road. And my team of researchers here, Rebecca Cole was the key person in my lab, did a PhD with me on this project. Seth Masters, another key person in Australia, helped us. Various people helped us with this discovery. And now there's 30 companies. 75 drugs are being tested, 22 in clinical trials, several based on this original drug that we had. And here's all the molecules, just to give you an idea again. I mean, the way drug companies depict things is if you get into the middle, it means the drug's now available in humans. Round the outside, it's different phases, and you're moving towards approval. All the dots here are different drugs that block different sort of aspects of NLRP3. Some of them are the one we found. And here's the drugs, again, for the chemists. That was the original compound. We made this one based on it. All these drugs are now developed. They're all kind of similar, you might say. And here's the diseases. So as we speak, different NLRP3 drugs are in trials for all these diseases. And the ones I mentioned already, MS, atherosclerosis, that's heart disease. Let's see, we've got osteoarthritis here. If we go around here, you've got colitis, you've got motor neuron disease, Parkinson's, the big one I mentioned, gout. You know, all these different diseases are being tested now. We're waiting, as you can imagine, with bated breath. And remember, many of these diseases I'm talking about get worse as you get old. They're inclined to be in older people. And a startling fact is 100,000 people in Japan are over 100. So what's going to happen now is as we all get older, the incidence of these diseases goes up. We don't know why. That's another mystery. Why are these diseases more common in older people? So we need drugs desperately as the population ages. I guess the way to think of it is things like vaccines and antibiotics means we're all living to a ripe old age. But the trouble is we're seeing an increase in these diseases as we live older to the older ages. So we need the drugs as a real urgency. And here's one area to think about if you're thinking of a future in science. Join us on this adventure. Become an immunologist. You can get stuck into these diseases. You can also work on cancer. You know, biomedical research is really important, but there's many aspects. You can do chemistry. You can do mathematics. We're using artificial intelligence all the time as well. All these are very relevant to this. So any branch of science can be extremely useful, remember, and you might end up doing any of these, really. But the message I want to give you is we need you desperately. We need more scientists to try to solve these really important problems. And it is through science that we'll solve these diseases. It's through science that will crack climate change, a second big concern, as you will all know as well. But there's many things you can do in science that are beneficial to people. So we need you more than ever to help us. And the excitement is there because of artificial intelligence, because of all these advances. We've got great tools now to use. I saw something just actually this morning. Artificial intelligence is like the microscope. Can you imagine when the microscope was invented? You could now see the germs, and that opened up a huge area. AI should enable us to really understand more and more about all these things in science, not just in immunology and many branches of science. And in terms of we're hoping for progress, two rival companies, Nothera, they have a drug to block NLRP3. They're reporting efficacy in Parkinson's. The drug Zydus, they're in India. They're reporting it in motor neuron disease. So we're waiting now to see if these drugs will work, and who knows, we might get lucky and some of these might actually work. And then when our discovery came out in 2020, actually, we first began to talk about this, and then Roche began taking our drug to the clinic. I got so many nice emails off people, you know, and I want to show it. This is why it can be very great. People can be grateful to us scientists, you know. I want to say a big thank you. I've been on various drugs, not symptom-free. You don't know the lease of life you give people. Well done in your work, placing inflammasomes, taking a great path, you know, therapeutic benefit. Thank you for the hope you bring. And that's what this really is all about. And as I mentioned earlier, Marie Curie said, science will banish fear. It also brings hope. And that's a very important thing. And in fact, during the pandemic, I was in the media a fair bit, encouraging people and saying, keep going, you know, follow the public health guidelines, take the vaccine. And a little old lady in her 90s sent me a little crocheted piece with hope on it. Isn't that nice to have in my lab? It's out there at the moment, you know, so we do bring hope. And of course, the ultimate goal of all of this science, remember, I don't know who's remembers Star Trek. Maybe some people are too young for that. The older people will. I'm a huge Star Trek fan, you know. The hope is the first Star Trek had a guy called Spock, and his message always was live long and prosper. So that's what science is all about, to help people to live long and prosper. And that gives you a little snapshot into my life as a scientist. And again, big congratulations to everybody. Brilliant that you're all involved in SciFest, the students and the teachers and the parents and everybody. It's a great thing to be doing. And again, congratulations to everybody and all the very best.